In this video, we are going to do problem number 32.0, binary search. So we are starting a new section, and this section has to deal with what is called generative recursion, also known as algorithms more formally. And this is going to be the hardest section of the course going forward. Why? Because generative recursion is going to require a lot more thinking compared to structural recursion, where we have the data definition and the recursive call just is rest of LST, right? It just falls out of the data definition over here. And we're going to see this shortly as we start this problem, right? So I do have the problem downloaded and open up racket. So let's just go down here. Notice that the design recipe right over here, it now includes a lot of generative recursion questions. And I recommend that you answer these, like type in whatever your answer is here, because it's going to help you think through the problem. All right, so let's just keep scrolling down and look for problem A. So problem A says, design the function linear search. It consumes a list of numbers and a natural number n, which is the number that we're trying to find. Produce true if the given number is in the list. Note, you cannot use any of the built-in functions like member question mark and etc. This is a structural recursion problem. All right. There's also problem B, which is going to be the generative recursion problem. But nonetheless, do pause the video and try to do linear search. Give us the signature, purpose, and some tests already. So it's your job to just template and code this out. All right. So pause this video and try to do this on your own. I'm going to go for spoilers in 3, 2, and 1. All right. I'm assuming that you guys took a good swing in it. Now let's go over together. So looking at these tests here, is the 7 in this list? Yes, it is. So just produce true right over here. -5 is not in the list of 8 and 4. So produce false. And is 8 in this list of 9, 3, and 8? Produce true, right? So simple enough. We have the stub here. We can comment it out. And you can either write the template or just grab it up here. Hopefully you guys should internalize this by now. And let's just rename this linear search. This linear search takes in 2 arguments, the list and then the number that we're trying to find. So that's called find num. And looking at these tests over here, given an empty list and the number that we're trying to find, produce false, because it's never going to be in the empty list. All right, so grab that false there, stick it there. And now comes the other part. So sometimes the number that we're trying to find is in the list and sometimes it's not. All right. So that can indicates that we need an if. All right. If the number is the number that we're trying to find, right, we have to compare them, then produce true. Otherwise, keep looking through the rest of the list, right? Do the natural recursive call here. And then this, of course, takes in 2 arguments. So if I were to run this code, it's going to say, hey, you need to be passed in the find num because linear search has 2 arguments. All right, so I run this code and it looks like all 4 tests do pass. All right. So now test, review, and refactor is the final step. So if you see this pattern, if, and then the Boolean, and then you produce the Boolean, you can usually simplify this to using or and for the combinator instead, right? So this if can be an or, and we can remove this true and run this code, and the exact same for test still pass. So why? Because or, right? Or as long as we get 1 true, it's going to be true, right? So this test, for example, 8 and 9, right? 8 is not 9, so it's false for the first one. Is 3 equal to 8? No, it's not the number that we're trying to find. And then finally, is 8 equal to 8? It is in this list, so we're going to get 1 true here. And as long as there's 1 true, this whole or becomes true. So that's why this works. All right. So notice how easy this function was to create in the sense that from this data definition template, we just copied, pasted down, and just filled in these 2 blanks mainly, and we're done. All right. That is structural recursion, because this rest call, this recursive call, is just on the rest of the list. It comes directly from the structure of the data, because cons, you have to take the first and then the rest, and you just recurse on the rest. Compared to generative recursion, which is problem B, it's going to take a lot more brain power, because we're still going to do recursion. You're still going to have a base case, but chances are that you're not going to recurse over the rest of the list. You're going to have to do more complex things and have multiple functions and combine things in different ways. It's much more harder, as we'll see shortly. All right. Anywho, let's just get started with problem B. So problem B says, design the function binary search. It consumes a list of numbers and a natural number n, which is the number that we're trying to find. Produce true if the given number is in the list. note that binary search only works if the input is sorted from least to greatest, right? This is very important. So for example, calling binary search with this sorted list, 5, 9, 10, 13, and 20, notice how all these numbers are sorted from least to greatest, and is 9 in this list? Yeah, it's the second element over here, so produce true. This would be a bad example, right? This is where the input list is not sorted. 13 is over here. Yeah, it's after this, before this 5, so this 5 should be first because it's the smallest, right? So this, we don't know what it would do. It could most likely produce an infinite loop or not find this number, as we'll see shortly. All right, it searches a number like humans searching a word in a dictionary, in that we open a book approximately in the middle and flip left and right as we get closer to what we're trying to find in a sort of zigzag pattern. And here is the description of the algorithm. So you're going to have to transcribe these steps. So step 1 is find the middle. Look at the element in the exact center of your current range. Step 2, compare. If the middle number is your target, then you're done. Step 3, if your target is smaller than the middle, you know that it must be in the left half. Step 4, if your target is larger than the middle, it must be in the right half. And step 5 would be repeat the half where the target can't be, and repeat the process on the remaining half until you find the number or run out of the list. And here's a huge hint. Use the built-in listref function. This is a generative recursion problem. Chances are your recursive call is not going to be rest of LST. Do not use any of the built-in search functions in Racket. All right? So we're talking about member, and there is a binary. There's like some other searches in there. I'm not sure. And this animation shows how binary search works. So let's actually take a look at that. All right, so here's the animation. I'm going to zoom in here. So there we go. So this is the list of numbers. We're looking for the number 9, and we're going to start from the middle. So we're going to grab the middle, which is 5. And since 9 is bigger than 5, we know that we can eliminate this entire half because it's never going to be on the left because this is a sorted list. So it must be to my right. And I'm going to pick some middle to my right, and then that was 7, and then that wasn't it. So I know that 9 is higher than 7, so I know it's to my right again, and like so, all right? So it's kind of like how we flip through a book, right? If I tell you, imagine if this book was a 200-page book, and I tell you to open your books to page, let's see, 169, right? How would you go about it? Well, if you imagine a physical book in front of you, you would open it approximately in half, right? We humans aren't really good at getting it half perfectly the first time, but you would get near 100, right? And you would, flip right because 169, that's the number that we're looking for. It is greater than 100, which is where we currently are. So I got to move rightwards, right? So I, take a bunch of pages and move to the right. Let's say I end up at 180, right? Well, yeah, I flip to the right and end up at 180. Well, now it's too far, right? It's way bigger than 169, so I gotta go flip left, and then let's say I end up at like 140. All right, we're getting closer to 169. I know that I'm like only 29 more pages there, so I flip to the right again, and I get to somewhere, let's say, 172, right? And then 172, I'm just a few more pages, so I gotta flip left again to get to 169. All right, so yeah, that is binary search in a nutshell. All right, by eliminating half the problem every time, because since the input list is sorted, right, you can eliminate half of the problem, right? We're looking for the number 9, so starting from 5, it's never going to be in the left half because it's a sorted list. All right, so here is the signature. They give us the signature. The purpose produces true if the number exists within the given list. So here's the number that we're trying to find. Assumes the list is already sorted. That's important. How? It searches it by eliminating half the problem at every step, like so. All right, so it's your job to do code. So do note that generative recursion problems, they don't really have a template in a sense, but this would be the template, but it's most often going to look like the structural recursion template, where you check for empty, but not all the time, right? So you can copy and use this as a reference. I'm gonna do that actually. I'll put it up here, but there we go. So yeah, this is what you're gonna essentially have to do, but more more accurately, you're gonna have to just transcribe this algorithm. Right, so I'm gonna paste this up here and then zoom in and then put it up here. All right, so I recommend you have the algorithm, in a separate tab or something, because you're gonna need to reference it because you're literally just transcribing this into code. All right, so pause the video and try to do this on your own. I'm gonna go for spoilers in 3, 2, and 1. All right, I'm assuming that you guys took a good swing at it. So now let's go over it together. So we actually forgot the test here. So let's actually write some tests for this. All right, so check expect. Let's do binary search of an empty list, and we're looking for the number 9. It's not gonna be in the empty list. So I'm gonna copy and paste this here. And let's do list 4. And 9, is 9 in this list 4? No. All right, let's do one that's passing for the one long list. This should produce true because 4 is in this list. All right, let's do a too long. All right, so too long, let's do the numbers 8 and 25. All right, is the number 25 in this list? Yeah, it is, so produce true. And we can do a failing test for that if you'd like. So false, this is gonna be -100 or -111, right? It's not in this list. All right, and then we can do the test that they gave us up here, right over here. All right, so scroll down here, check expect. This binary search is going to be true. All right, is 9 in this given list? Yeah, it is. It's this element. All right, so I'm going to run against stub here. We get some mismatches, no other errors. And now, really pause the video. And again, hopefully this should be all the mental scaffolding needed to solve the problem, right? To write the code. I'm going to go for spoilers in 3, 2, and 1. All right, I'm assuming that you guys took a good swing in it. So now let's go over it together. So I'm going to scroll up here and let's grab the structural list template. All right, it's wrong in a sense that there are going to be many pieces that we're going to remove and adjust. All right, so I'm going to rename this binary search. This takes in 2 arguments, the number that we're trying to find, right, and the list itself. All right, so given the empty list, we still have this base case. This base case is actually still valid. All right, we have to do something when we hit the empty list. So it's going to be false. All right, sometimes you're going to have to come up with the base case yourself. But in this case, we're processing a list, and usually that involves just checking if the list is empty or not. All right, so there we go. So that's going to produce false because 9 is never going to be in the empty list. All right, so now comes the hardest part. All right, we're going to transcribe this algorithm over here in code form. All right, so find the middle, step 1. Look at the element in the exact center of your current range. So current list. So this is our current list, and this is the number in the exact center, right? This is 5 elements long list. 1, 2, 3, 4, 5, and the middle is the number 3. Right, so we're not going to do anything with the first of the list here, right? Already this structural recursion template is not really helping us in a sense. It does give us the recursive structure in a sense of the base case, but we're not going to use the first of the list. We're going to start from the middle because that's what binary search is. All right, so this is where listref comes in. All right, listref, it takes in first, I recommend you go to the documentation, but it takes in the list, takes in a list, and then an index. How to get to the element, right? So this would be 0, 1, 2, right? So we want the half of this list. All right, so we need to get the index of it. So we're going to divide the length of the given list by 2. That's how we get the middle number. All right, so that's going to be this thing is going to be the middle number. And step 2, compare. If the middle number is your target, then you're done. So this is our target number, and you want to compare them. And if they're equal, right, then we're done. Produce true. Otherwise, we have to go do another if and another if, right? So it looks like this whole thing has 3 ifs, 1, 2, and 3. All right. So multi-case if, that is kind of just a cond. So this can be just cond, and then I'm going to just wrap these around square braces. All right. So if it is equal to, if the middle number is our target, then you're done. You're done meaning that it is the number that we're trying to find, so produce true. All right, otherwise we have to look left and right depending on if it's bigger or smaller than the number, all right? So if the find number is bigger, then this middle number over here. All right, then we're gonna have to do something. All right, this would be searching the right half, because we know that it's bigger, so it must be in the right half of the middle number, right? So we have to do the same thing for the left half. All right, so I'm kind of doing this first and this second, but it doesn't really matter, right? Steps 3 and 4 can be swapped. So there we go. Just gonna paste this in, and this is gonna be looking in the left half. Left half. All right. So we still have to do a recursive call. All right. So this is where it drastically differs. All right. So before we do that, actually, notice how this is repeating. Listref LST length divided by 2. Listref LST length by 2. This is all dividing by 2. Let's actually wrap this into a local and make it so that we can see the meaning at a glance, right? Because this, when people look at it, it's like, we're dividing the length by 2, and then, yeah, we can give it a name, and it will be more readable. So we're going to do a local here and define it to be the mid num, because that's what it is. All right, this is going to be the middle number, like so. All right, and everywhere we see this, replace it with mid num. So there we go. There we go. And then there we go. All right, much more better. All right, so the find number is greater than the middle number, then we have to go search to the right. Otherwise, if it is less than, then search to the left. All right, so we were back at building the recursive call, right? So this is gonna have 2 recursive calls. All right, and I'm going to indent those. Control I to indent, always, whoops. All right, and it takes in 2 arguments. The find number is gonna stay the same. Right, the number that we're trying to find is not going to change, but the binary search has to go get the right half, right? So right half of list. And then this would be left half. Half of the given list. All right, so these 2 helper functions we're going to have to design. Those are going to be structurally recursive. Most functions actually in real world programs are structurally recursive, and it's a few that are generative recursive, like this one. All right, so I recommend you pause the video and try to do the right half and left half of the list, right? How would you get those out? All right, so try to do that on your own. I'm going to go over spoilers in 3, 2, and 1. All right, I'm assuming that you guys took a good swing at it, so now let's go over it together. So getting the right half and the left half of a list is really just described in the functions drop and take from 31.01 and 31, right? Take and drop, which you should have done before, right? So we can just paste in these definitions. I don't want this video to be too long, but this is the functions that we're going to need, all right? This take would get the first n elements. So given the list 948, if we take 2, then 1, 2, we're going to exclude this 8. So this is going to get the first left half, and then drop is going to get the right half, right? So given the list 9, 2, and 4, if we want to take 2 from this list, drop 2, then we're going to drop 9 and 2, and then we're going to be left with the list 4, right? And if we drop empty of 100, it's just going to give us empty. All right, so that's what we're going to need here. And notice how take and drop take in 2 numbers, right? The list and then the number being the elements that we want to drop, right? So we're going to drop up till the middle, right? All right, so given this is going to be drop, right? Because we're searching the right half. So we're going to drop all the left elements, all right? Because we know that everything to my left is not going to be the number that we're looking for, because it's because we're greater than, it's the greater than case, right? As these instructions here. All right, so this is going to be drop, and then we're going to give it the index, all right? So it's going to be this here essentially. So this index, drop the right half of the list, and then this is going to be take the left half. All right, so if we run this code, looks like we have an error here, and I think it's because this should be inside this parentheses block. All right, there we go. Run this code, and looks like we get an error over here. Listref expects a non-negative integer given 2.5. All right, so what is the problem? given 2.5. So this is the length of the list, 1, 2, 3, 4, 5. We divide that by 2, we get what? We get 2.5. So that is probably the issue. List ref, right? List ref takes in the list, and then we gave it 2.5. So what we have to do is we actually have to round this index down if it's a decimal. So this index has to be rounded down. So floor, right? And then likewise, everywhere we see this, we have to floor it. So let's actually factor it into a variable. Mid index. It's going to be this. Mid index. That. And then this. Like so. Run this code. And looks like we have an infinite loop. Is one of these lists not sorted? It is. 1 second. All right, so I found the bug. What you need to do is comment out all the tests and just run through them one by one until you find and isolate the failing test that's causing an infinite loop. So in this case, this would be the test that is causing the infinite loop. So let me just show you why. So I'm gonna move this to another monitor, like so. And if I run this, it's gonna result into an infinite loop. And how you can deduce this is you can use the debugger. So switch the language to ASL. So you can use the debugger. So I'm gonna scroll down here really quickly. So where is it? This test over here. Debug. And then you have to put pause on this. You have to do it quickly because it's gonna infinitely loop. Debug again. And then hopefully we see the green arrow. All right. And you might have to hit go or debug again to get this green arrow to pop up. But you should do it quickly because it's gonna infinitely loop. If it does infinitely loop, right, it's gonna lag your computer. So just keep spamming Control R. Until you can set the breakpoint. But this is why it infinitely loops. So let's actually step through this function. Right, so we're trying to find 9 in this list 4. So we're going to call binary search. And we're in this cond. Is this list empty? No, there's a 4 in here. So we're not going to hit this branch. We're going to hit this else branch instead. This else branch has a local, and we can step through it. So here is the floor, getting the middle index by taking the length of the list. In this case, there's only one number in this list, so that's going to be divided by 2, which is 0.5. Flooring that gives us 0, right? So we should see the middle index here being 0, right there, right? So let's just keep going. So the middle number is going to be list ref of the list, which is just 4, 0. So this just gives us that 4. So that's the mid num for the number that we're trying to find is 9. So is 9 equal to 4 in this branch? No, it's not. So we're going to go to the other branches, right? Is 9 greater than 4? Yes, it is. So it must be in the right half of the list. In this case, we only have the list 4, so there kind of is no right half, right? So step, there we go. Drop list 0. So list and then 0, because the middle index is 0. And if we step through that, drop actually does its job correctly, right? If it's 0, then we produce the list. And that is the bug, actually, right? So because if you give drop 0, then it's not going to, drop the list. So we're going to loop back around to binary search, and the list is not small. It's still 4. The 4 is still in there. So that's the bug, right? So if you follow the green arrow, we're just going to infinitely loop after we hit this point, right? And you can actually set a breakpoint there, hit go, and then we can see hit go again. That's the next iteration. That 4 is still there. Hit go again. That 4 is still there, right? So yeah, it's because every iteration, each time we do a recursive call, the list is never getting smaller because we call drop with 0, all right? So we need to fix the call to drop. The drop function works fine. We just really shouldn't pass 0 to it, all right? Because it's bugging out when it comes to this list. When it comes to other lists, it seems to work fine. And let's just actually elaborate why, right? So this over here. So I'm just going to come out this test again. And I'm going to define this to be x, right? All right. So let's say that we're looking for the number 13 in this list. Well, it's going to be on the right half, right? So we start from the middle number 10, right? And since 13 is greater than 10, we know that it's going to be on the right half of this list. So we call drop, right? We call drop the middle index, which is 0, 1, 2, right? So there we go. Notice how it's still including this 10 though, even though this was the middle number that we just compared to deduce that it's in the right half, right? So that was more or less the problem. This middle index really shouldn't be 0. It should be rounded up for one element long list, right? And likewise, same with this test over here, right? We want to round this 2 to a 3 because we just compared the 10. Right, so that's what we're going to do. So instead of flooring this index, half of the list, we can round it up. So this is going to be this, but sealing to round it. I think sealing. There we go. So if I uncomment this test, that fixes that. And let's make sure that it passes all these other tests and doesn't infinitely loop. All right, and all 14 tests pass, and we fix that infinitely loop. All right, so notice how much harder this was compared to our structural recursion problem that still just searches the list. Right, this linear search, it works on unsorted and sorted lists. That's one of the main benefits. And it was much simpler to write. We just copied this down, tweak these dot dot dots. This dot 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 was a false. This was an or, and then we're done. Right, do the recursive call, we're done. Compared to binary search, right, we had to transcribe this entire algorithm, and notice how I made a mistake with drop, right? I didn't realize that there was an edge case that for searching the right half, we actually had to round this up instead of rounding down all the time for the middle index, right? And that resulted in an infinite loop. And infinite loops are common in generative recursion problems. You have to be very careful. And you have to really, this is why the questions over here this is why there are questions over here in the design recipe, because this will help you really elaborate and hopefully catch those edge cases so you don't get confused. But that's how you debug it, right? You switch to ASL, get the debugger, and pause and set breakpoints, right? But anywho, that is pretty much problem B done. All right, so now let's actually compare the two and benchmark them. So linear search versus binary search, this animation shows the differences between the two. So let's just copy and paste this URL and paste it in here. Right, and it shows the animated differences. So on the bottom is linear search over the same list, right? We're looking for the number 37. In linear search, we'll just go through every number, left to right, one by one, until it finds 37. All right. Compared to binary search on the top, we start searching from the middle, and immediately, since we know that 37 is greater than 23, we eliminate this entire left half. All right, and then we keep going left and right depending on whether the next number is bigger, right? So we just eliminate this entire left half. 41 is greater than 37, so it's not going to be on my right, it's going to be somewhere to my left. And we keep having it at every step, all right? Compared to linear, which just goes one by one every time. So we can actually see how fast this is by doing these benchmarks, all right? So let's just start small and then go big. So starting from 10, this is going to build a 10 element long list of even numbers that are sorted. The middle number here is 10. So if we linear search this, it's going to go 1, 2, 3, 4, 5, 6, right? Roughly 5 to 6 times until it hits the number 10. So it's going to be half this every time we do a search, right? So these are quite small lists. We're going to see difference when we have a bigger list, right? So let's say 100 elements. Bench list is this, right? So this is 100 even numbers. And the middle number here is 100. So this one over here. So linear search, again, is going to go sequentially, and it's going to go 50 times roughly to get to this 100. All right. So how fast is that? Well, we're actually not going to see a difference until we increase this to 10,000. Well, 1,000 first. 1,000 is still too, we actually see some differences here. So half of 1,000 is 500. So linear search of this, it's going to be 500. In this case, it ran faster, so it's kind of strange, but that is the way it is. Sometimes DrRacket makes it faster, right? If we run it through 10,000, then we should actually see some differences, right? Half of 10,000 is 5,000. So it takes 6 milliseconds. Just run it again, right? 6 to 8 milliseconds compared to binary search, which is 3, right? So binary search is much faster when it comes to bigger and bigger lists. When it comes to smaller lists, like maybe 100 to 1,000 elements-ish, then linear search is actually faster because that's just the way it is. It's also because the code is smaller, so the computer has less instructions. But Anyways, let's just recap what we did in this video. All right, we did a structural recursive problem and noticed how it just fell out of the data definition comment, and we just had to, make these ... dots false and or, and then do the recursive call over the rest of the list, and then we were done, right? It was much more easy compared to the generative recursion problem, which was much more complex, right? This algorithm, we kind of had to rearrange the problem into several sub-problems and then combine the solution. And yeah, it was a lot more work. We just made a bug by this over here and etc. Right? So again, most functions in the real world programs are structurally recursive, and there are some generative recursive functions that we wrote. And we wrote this because it's faster over, searching over a long list, right? There are problems where generative recursion is the only way to solve a problem, as we'll see in the upcoming sections, right? But anywho, you learned what the differences between structural and generative recursion is. You still do recursion, you still have a base case. It's just that you have to combine, and you're not necessarily just gonna recurse over the rest of the list all the time. Sometimes you will, but in this case, we have to do much more complex thinking, right? We have to transcribe an algorithm. And this comes from domain knowledge, right? We're gonna get domain knowledge from math and from transcribing descriptions of an algorithm, which takes a lot more brain power compared to structural recursion, where we just dropped things straight from the template down. All right. Anywho, submit this into Handed and check your score. And that is about it for this video. And I'll catch you in the next one.